It's a Sunday evening. Fred is playing soccer with his friends when suddenly the ball fell into a puddle of mud. Well, that's quite unfortunate, isn't it? Fred, being a fan of efficiency, wonders what is the shortest path to take to retrieve the ball? Well, usually the shortest path between 2 points is a straight line. Or is it? The line short is under the assumption that Fred's velocity will remain the same. But since we're dealing with two mediums, cement in the mud, it will not be the same case. Does he travel this way or the other way? A way of answering this question would be to use Fermat's principle, which states that light travels between 2 points in the least amount of time. As we all know, light travels approximately 300 millimeters per second in the void, but it's not the same case in a different medium. We define a coefficient of refraction n, which equals c over v, with c the speed of light in the void and v the speed of light in that medium. When light travels into different mediums, the phenomenon of refraction happens. It describes how the light changes its trajectory dependent on the refraction coefficient. In the case of two mediums, Snell's law gives us the trajectory of least time for the light to take from a point A in the first medium to point B of the second medium. We can observe the changing of light's trajectory using a very simple experiment. We're gonna need a pierced bottle of water at one side where the water jet flow is laminar, and we're gonna need a laser. When we shine the laser through the pierced bottle, we can observe light bending in the jet of water. Optical fibers as such use the same principle to redirect light and allow for fast information transfer. With different refraction coefficients, we can observe different phenomena. If the refraction coefficient was increasing in a linear fashion, light will curve in a different way that will allow the phenomenon of mirage. In the desert, high temperature leads to the variation of the air density, which causes a gradient on the refraction coefficient. This allows the light to curve from the sky to the eye and makes the eye see an image of water on the ground. It is simply an illusion of the image of the sky on the ground. Another example of a problem that uses Fermat's principle is a brachistochrone. Let's take a rolling object at point A and it falls under the force of gravity to a point B in the least amount of time. What is the best trajectory to achieve this? Well, this problem was first posed by Johann Bernoulli back in 1696 and was solved by Newton, where he proved that the best path is the roulette, the curve you get from a point in a rolling disc. With all that being said, now Fred knows what trajectory is best to follow and needs to curve his way out. Thanks for watching.